Hey, finally, let's take a look at an encryption scheme that actually kind of has this ability to encrypt longer messages natively. So we've just seen for RSA, for example, if we want to properly encrypt stuff with RSA, we either need to use the hardcore bit, in which case we can encrypt a single bit, and then with the extended from the lecture also multiple bits, or we can go the random oracle route. But in this case, we need random oracles, which is kind of a more extreme assumption. So now let's take a look at an encryption scheme that actually has capabilities to do longer messages baked into the thing. Not something that we add later on, but it's what it can do. And this encryption scheme is ElGamal. So in this setting, we need a prime order group G again. Our secret key will be a random exponent, and our public key will be mostly G to this random exponent. Then to encrypt the message, I basically do the same thing as we usually do. We take the message and we blind it with some random value. And then we give the guy who should be able to decrypt it, we give him some hint that should help him in decrypting. So if I only take a look at this part, then this is like a one-time algebraic one-time pad version of M. So I just multiplied it with a random group element, and well, in this case, it's a random group element, the result. But then to make it decryptable, I also provide G to the R in the ciphertext. How does this help? So how can I now decrypt M if I have the secret key? Well, I take the G to the R and I raise it to my secret key. Now I have G to the SK times R. And then I just divide the second part of the ciphertext by that. Okay, so basically I take the G to the R, I add my secret key to it, and then I divide this whole thing by G to the R times SK. And then this will cancel out. So I get my message. And now if we want to prove this secure, we need some sort of assumption about these groups that we have here. So for example, something like the discrete logarithm assumption should be hard. However, as you maybe can imagine, just the discrete logarithm assumption won't be enough for this, because the discrete logarithm assumption is like a computational assumption. And if we want to prove something like indistinguishable ciphertexts, we need an assumption that doesn't just tell us, okay, you can't compute something. You need an assumption that tells us something like, oh, you can't distinguish this from this. Our workaround in previous schemes was kind of to go to the hardcore bit, and then the hardcore bit is just a single bit. So there, it's kind of the same whether I can distinguish whether or not I give you the correct hardcore bit or just compute it outright. Because if I know whether or not 0 or 1 is the correct hardcore bit, I can also just compute the hardcore bit. But this is not the same for like D-log assumptions. If I give you a candidate discrete logarithm, you can just check whether or not it's correct. But if I give you a wrong one, then it doesn't help you to actually compute the correct thing. So the discrete logarithm assumption won't do because it's like a compute this assumption. We need a this cannot be distinguished from this assumption. And I'll just sketch it roughly here because it's not that important for this lecture. I just wanted you to see like a proper encryption scheme once. And this assumption says the following. If I choose random A and B, and then I give you G to the A, G to the B, and G to the A times B, then you can't distinguish this from the scenario where I give you G to the A, G to the B, and a random group element R. So in this assumption, most of this stuff is the same. The important part is like you can't distinguish whether I give you a random group element or I give you a group element that is kind of linked to this G to the A and G to the B, in the sense that the two D logs in G to the A and G to the B are multiplied in the exponent of G to the A times B. Notice that one way to actually break this assumption would be to compute the D log of G to the A. Then I would get A. And then with that A, I could easily compute G to the B times A using this part. And then I could just compare whether this is equal or not, and then easily distinguish whether I got the G to the A times B or the R. But because we think D-logs are hard to compute, this route of attack is kind of impossible. But more than that, we assume that it's even also hard to distinguish G to the A times B from R. And now the proof is also not that difficult. Basically, we're using A is equal to SK, and we use B for the randomness of the challenge ciphertext. Then you can already see there's like this G to the AB here in this thing. And then you can easily argue that this G to the A times B, this is indistinguishable from R. And if I just gave you R times M, then you get no information about the message because it's the message multiplied with a random group element. So that's kind of the intuition of ElGamal encryption. I don't want to get into the details too much. But it works similarly to things we've seen before. Basically, we take this value here and then replace it with a random value. And then we can argue that if we replace it with a random value, the adversary has no chance of winning. And then we just need to argue that the adversary cannot distinguish in which of these two cases it is. And if it cannot distinguish in which of these two cases it is, then it's impossible for it to win more in this case than in this other case. So that's it for ElGamal encryption, where we have this nice thing that messages are not just 0 or 1 or something, they can just be any arbitrary group element. And if we have a prime order group where the discrete logarithm is hard, then this prime order is pretty big. So we have a lot of group elements that we can encrypt. Thanks and see you.